With exercise 1013, we're going to be looking at hydrohalogenation of alkynes, and then see how that's kind of the reverse in a way. That and halogenation, those are the reverse of elimination reactions that create alkynes. So you can sort of think of them as a two-way street. To create the alkyne, you do an elimination, and to turn the alkyne either into an alkene or an alkane, with halogen leaving groups on it, you can either do hydrohalogenation or just regular halogenation. Remember, hydrohalogenation has two types. You can either add just a regular hydrogen and one of the halogens. Remember, the halogens in group 7a, fluorine, chlorine, bromine, and iodine, to just talk about them generally, you use a capital X. So that capital X means any of the halogens, only the halogens. Sort of like a capital R means any carbon chain. So recall that if you just have hydrogen and a halogen, that's a Markovnikov addition. So if you don't have any peroxides, you just have hydrogen and halogen, it's Markovnikov. So the hydrogen goes on the less substituted carbon, and the halogen goes on the more substituted carbon. Notice here, this carbon on the end is only bonded to one other carbon, so it's primary, and this carbon in the middle is bonded to two, so it is secondary. And notice where the hydrogens went. They went on the primary carbon. Notice where the halogens went, the secondary carbon. So that's Markovnikov addition. Hydrogen goes to the less substituted carbon. If you want to do anti-Markovnikov addition, so that the hydrogens go to the more substituted carbon, you can use the same recipe, just add peroxides, ROOR. Okay, so that's what we can do. Now we did that with alkenes, we can do that with alkynes. It just adds two equivalents. So you add H and X, and H and X, and they go to the same positions, either Markovnikov or anti-Markovnikov. The fact that you add two means that you have to add excess of the reagent. Now those two letters are just standing for the English word excess. So it's sort of an abbreviated way of saying that. So you just have a whole bunch of the reagent, so it can add twice. And that's what's happening here. We have an alkyne in A, and we're going to add two hydrogens and two halogens on here, because we have excess hydrogen and halogen. The halogen we're going to add is chlorine. Now if you think about the two carbons in this triple bond, the one at the end is primary and the one in the middle is secondary. Because we don't see peroxides, this is going to be Markovnikov addition. And we can sort of model it on the example in that recipe sheet. And here, if you're ever in doubt about the number of carbons, always number them. So you can see there's 1, 2, 3 carbons on this chain outside of the ring. 1, 2, 3 carbons. It's especially important because as you go from triple bonds, which are linear, to single bonds, which are tetrahedral, it looks a little bit different sometimes. So notice we're going to put the hydrogens and the halogens on carbons 2 and 3. Because this is Markovnikov addition, the hydrogen will go on the less substituted carbon. That is carbon number 3. That's primary. So we're going to have 2 hydrogens here. Now there's more hydrogens there. There was one hydrogen there to begin with. So there's technically 3, but we added 2. So just to be clear about the change we're making, I'm going to just draw those 2 in. In addition to that, on carbon number 2, we're going to add our 2 halogens, the 2 chlorines. And so just from the perspective of synthesis, that's your product. That's all you'd have to draw in this particular reaction. You'd see the recipe for hydrohalogenation, you see an alkyne, so you say, okay, I'm going to add 2 equivalents of this, and it's going to be Markovnikov. So you redraw the molecule, you draw the 2 hydrogens on the less substituted carbon, the 2 halogens on the more substituted carbon. Now for this first example, I'm going to go through the mechanism for how that happens. I won't do that for the future ones for the sake of time. So if you're not interested in the mechanism, it's not one that you'll need to draw on this test, but it's one that may make it easier for you to remember the reaction. If you're not interested, you can scrub down to where you see B. But otherwise, I'm going to go through this mechanism quickly for us here, because it's the first time that we're talking about the hydrohalogenation of alkynes in a video. So the first equivalent you have is you have a hydrogen And here you have a chlorine, that's your halogen. We know that these pi bonds are nucleophiles. Pi bonds are one of the 4 nucleophiles you'd want to recognize. The full negative charge, partial negative charge, lone pairs, or pi bonds. And so those can attack an electrophile, and the only electrophile we have here is the chlorine, or is the hydrogen, which is slightly positive because it's losing electron density to this chlorine. So one of these pi bonds can attack the hydrogen, kick the chlorine off, so that's proton transfer. We now no longer have that triple bond. We have our 3 carbons, 1, 2, 3, 1, 2, 3. The hydrogen goes on the less substituted carbon. Notice we've only used 1 pi bond, so the other one should still be there. And we have a carbocation on the more substituted carbon. And that very quickly is very quickly attacked by the chlorine that left. That chlorine has a full negative charge, this one, and after it leaves, and so it attacks that carbocation. And notice that's nucleophilic attack. And that should look really familiar, this so far. This was the mechanism for hydrohalogenation that you would have drawn on a previous test. So after that, what you end up with is this. And if you only add 1 equivalent, so if you don't see the excess here, that's your product. Just you have the alkene still, and the hydrogen goes to the less substituted, chlorine goes to the more substituted. So if you only have 1 equivalent, or if you don't see excess, then this would be your product. But because we do have excess, we have another HCl. Because we do have excess here, we have another HCl in the beaker. And this second pi bond can act as another nucleophile and attack the slightly positive hydrogen of another HCl molecule. So this pi bond can attack that hydrogen, kick the chlorine off, and what you end up with there is the hydrogen goes to the less substituted position again to create the more stable, more substituted carbocation, and then the chlorine that had left, that chlorine comes back and acts as a nucleophile to attack that carbocation. So it has a full negative charge that attacks that positive charge there, and you end up with your product. And notice that that is exactly what we had predicted when we drew that earlier here. So there are sort of 2 perspectives you can view this reaction from. You can view it from synthesis, where we jump straight to this product, just knowing what happens. And then there's the mechanism, where you use curved arrows to show how electrons move to create that transformation. I think it's worthwhile walking through the mechanism at least once, because it will help you remember why you get those products that you do. And so it'll remember what products you get. Now that we have that down, though, for that reaction, the next time we see hydrohalogenation, I'm not going to draw the mechanism for it. We'll just do it from the perspective of synthesis. Okay. Now in this one, we have a slightly different recipe. The halogens are already on the molecule, and when you see halogens on a molecule, you should think in your mind, a lot is open to me. I can do substitution, or I can do elimination. Now, I could substitute 2 things, or I could eliminate 2 things. Remember that every time you do elimination, you create a pi bond. You could do elimination once, and then you could do elimination a second time. That means you can create 2 pi bonds here. In other words, you can create an alkyne. And so that's what happens. If you have a halogen on neighboring carbons, or if you have a halogen, if you have 2 halogens each on neighboring carbons, or if you have 2 halogens on the same carbon, like we have here, In both of those cases, you can use excess strong base, followed up with water, and it'll give you an alkyne. Now, we've drawn the mechanism for this in a previous exercise, in a previous video, so I'm not going to walk through that long mechanism again. But I will show you how you can translate this thought process and apply it to this specific reaction. So it doesn't affect the 5-membered ring. It's only going to, the base is just going to affect the leaving group. So the ring stays the same, these carbons sort of stay the same. When you're first drawing this, it's okay to just copy down the carbon skeleton. We'll adjust it as we make changes. This strong base, sodium amide in liquid ammonia, is going to eliminate both of these leaving groups. Each time one of them gets eliminated, you create a pi bond. So when you eliminate one, you create one pi bond, eliminate the second, you get the second pi bond. This hydrogen at the very end is acidic, so this base steals it off, and it's to put another hydrogen back on, that we have the water there. So we discussed that and drew the mechanism for that quickly in a previous video, so I won't go through that again. But here we have, this is really our product. Predicting our product is as simple as that. The problem is this is not the right shape. This is a misleading shape because these triple bonds need to be linear. So once you have it drawn out, redraw it with the correct shape. And that's your product. So notice this has the correct shape, and that's the product you would get if you mixed these two things together, or three things together. Okay. So next, we have C. And in C, we're adding excess hydrogen and halogen, or an excess hydrohalogen. And so this is very similar to the first reaction we drew. Count the carbons to make sure that you're drawing the right number. So 1, 2, 3, 4, 5, for example. And I'm numbering these not to name it, just to keep track of stuff. So I don't have to be as strict about where the number should go. I'm just keeping track of stuff. So here, if I redraw 5 carbons, 1, 2, 3, 4, 5, and I number them, then I know where to put this methyl group. It goes on carbon number 2. And I know where to put the hydrogen and the bromine. They're going to be between carbons 3 and 4. Now, where does the bromine go? Where does the hydrogen go? There's no peroxide here. And so if you don't have peroxides, it's Markovnikov addition. The hydrogen goes on the less substituted carbon, and the halogens go on the more substituted carbon. So out of 4 and 5, the carbon at the very end is primary. The carbon sort of at carbon 4 is secondary. This is bonded to 2 carbons. And so the hydrogens will go at the end. The 2 hydrogens that you add here will go at the end. And the bromines will go on the more substituted carbons. And the reason for that is because these carbons allow you to form the more stable carbocations in the mechanism, which we drew above. And so that's it. From the perspective of synthesis, that's how you would predict the product for this. You'd redraw the molecule with the correct number of carbons, everything placed in the right way. You'd look at the recipe, see what you're adding, and then think of how you're adding it, Markovnikov or anti-Markovnikov in this case. And another thing to notice is how this hydrohalogenation, and halogenation in general, is sort of the reverse of elimination. In elimination, we are taking a molecule that has 2 halogens on it and taking them off, creating an alkyne. Notice what we're doing in this other reaction is taking an alkyne and creating a molecule that has 2 halogens on it. And so these are sort of the reverse of each other. All right, let's try D. What we see here is a molecule that has 2 leaving groups. You see 2 leaving groups and you should think, I can do either substitution twice, or I could do elimination twice. Or maybe I could do a mixture of the 2. What recipe am I mixing this with? I'm mixing it with excess strong base. Strong base and leaving groups, that's a sure sign of an elimination reaction. And because there's excess, you're going to do 2 eliminations. You're going to eliminate both of those leaving groups. So you can draw that molecule in. Notice that it has 2 carbons on that chain there. So 1, 2. Now, you can copy it down exactly as it is and then draw the carbons in. When you eliminate the first leaving group, you get the first pi bond. When you eliminate the second leaving group, you get the second pi bond. But this is technically not the right structure because it has the wrong shape for the triple bond. You have to redraw that so that the triple bond is linear. So that there. Now this has a hydrogen at the very end that's kind of acidic, which we'll talk about in a future video. The base would steal that off. This water here is there to put that hydrogen back on so that this isn't left as an anion with a full negative charge and a lone pair. And so that's how you can do that's how you can predict the product for this. And we aren't drawing the mechanism, we're just thinking, what product will we make? What can I synthesize as a molecular chef with these ingredients? So anytime you have a dihalide, if the 2 halogens are next to each other or if they're on the same carbon like they are here, and you're mixing it with excess strong base followed by water, remember to include those numbers for the steps. In those cases, you create an alkyne. Every time you do an elimination, you create 1 pi bond. We can do 2 here, so we create 2 pi bonds and get an alkyne. Oh, and this should have those lines in the middle. This is a special molecule called benzene, so because they're there in the beginning. Okay, let's try E. Now with E, we're combining these reactions. You see this molecule here, you see 2 halogens, and so you're thinking, elimination, or maybe substitution. But I could do it either of those twice, because I have good leaving groups. When you look at your recipe, you see a lot of stuff. The first thing you'd see is that you have a strong base followed by water. And that's exactly what we did last time. That's an elimination. So we can take this molecule where the 2 halogens were. For each halogen, you could get a pi bond after you do the elimination. So in this first step, if you just treated it with excess sodium amide, that strong base, you would end up with the pi bond, but also in addition to that, it would rip the hydrogen off here. Notice that this carbon has a hydrogen there. The base would rip that off, and those electrons would become a lone pair with a full negative charge, which is unstable. Now this is technically not the right structure because the triple bond is not linear. It needs to be. So if you need to draw that just as a sort of rough draft, completely fine. Just make sure that you go back and correct it with the correct shape of the molecule. The shape is not incidental. The shape determines what pockets this molecule can fit into and how it will behave, what molecular engines it could possibly turn on. So it's really important to draw the correct shape. Without the correct shape, the product you're predicting is technically incorrect because it wouldn't react in the same way. Now this is very unstable, and that's why we have this water here. Water provides a hydrogen. You can do a proton transfer, and so ultimately that puts the hydrogen back on. And we could jar it in, but really it's implied in these skeletal structures so long as there's no lone pair of charge there. And so that's what we get after the first 2 steps. So after those first 2 steps, we've done the elimination, we have this alkyne. But we aren't done, because we have another step here that they list. That second step, you see a hydrogen and a halogen, hydrohalogen, and a peroxide. That is the recipe for anti-Markovnikov addition of H and X. So hydrohalogenation, anti-Markovnikov. Notice that they don't write excess in. So when you add that, just as we have here in the recipe, and as we drew in a mechanism early on, although with these peroxides it's actually a mechanism that uses something called a radical that we'll learn about in the next chapter. But what you end up doing is adding the H and the halogen, in this case the H and the Br, and you do it anti-Markovnikov. So we still have the ring. We still have two carbons. We're going to use the glue from one of them to stick a hydrogen and a halogen on. One of them will stick the hydrogen on, and the halogen will come in as a nucleophile. Oops. And because there are peroxides present, the hydrogen goes on the more substituted carbon. Here, the secondary carbon rather than the primary one. And so you'll get this product. Now, technically, you would get a mixture, because you'll notice that here we have the cis product. There's no reason for you to, because you have that, in this case you would end up getting a mixture of the cis and the trans. And actually you would probably have a larger amount of the trans product, because these are big groups, and so they're more stable when they're not forced to be close to each other, pushing against each other, repelling each other. So you'd get a mixture of these two products as the result of these three steps. The first two steps were elimination. You eliminated both of your leaving groups. You created two new pi bonds. Once you have that alkyne, the third step was adding H and Br anti-Markovnikov. Now, that takes the alkyne to an alkene. We added H and Br, the H on the more substituted carbon, the Br on the less. We just had to think a little bit about stereochemistry at the end to make sure that we got both the cis and the trans product. Okay, F. F is a similar case. We have three steps total. We look at our original molecule and we see two halogens, and what should pop into your mind when you see that is that you can either do substitution twice, elimination twice, or some combination of the two. To know which one, you look at the reagents, and here we have excess strong base. So that's a sign that we are going to do an elimination. We have excess strong base followed by water, as we can see in this recipe, and as we've seen in previous exercises. When you add excess sodium amide, NaNH2, and the solvent here, this dash NH3 just means that ammonia is the solvent. When you do that followed by water, you end up with the alkyne. And be careful, make sure you put the numbers in front of these steps, because if you mix all this together, these reagents will react with each other rather than with the carbon chain, which is what you want. So that ring stays exactly the same, and we end up with, if you want to draw it first in the same shape, you can. Just make sure you go back and correct it. One of the leaving groups leaves, you get one pi bond. The other leaving group leaves, you get the other pi bond, and you get this alkyne. Now you just want to correct it so that it's the right shape. Otherwise, you'll predict it fitting into the wrong pockets and reacting in the wrong way, or in areas it actually wouldn't react in. And so after you do that, use that excess strong base in water, you've done two eliminations, and you end up with this alkyne. And it's that alkyne that you're going to treat with excess hydrogen and bromine, here, hydrobromic acid. So we don't see any peroxides here, and therefore it's going to be Markovnikov addition. So if we treat this with excess hydrogen bromide, or hydrobromic acid, we're going to still have that ring. We'll still have two carbons, 1, 2, 1, 2, but we're going to add two hydrogens and two bromines, and they're going to add Markovnikov because there are no peroxides, so the hydrogens go on the less substituted carbon, and the bromines go on the more substituted carbon, so that this would be your product. Overall, and notice what we've done. We've replaced the chlorines here with bromines. That's our overall change. Notice how these two reactions, elimination and hydrohalogenation, reverse each other. So you can use elimination to create an alkyne, and you can use hydrohalogenation to turn the alkyne into a halo, or a dihalo alkane. Okay, so that hopefully gave you some practice with doing the elimination reactions to form alkynes, and then using hydrohalogenation to create halo or dihalo, haloalkenes or dihaloalkanes.